At 3:47 a.m. on January 18, 2026, California lost a piece of itself. Not metaphorically, not symbolically, physically. A 150-meter section of Highway 1, one of the most photographed roads on Earth, detached from the cliffs near Big Sur and collapsed into the Pacific Ocean. Pavement, guardrails, and centuries-old rock vanished in less than 90 seconds, plunging nearly 300 feet into darkness below. There was no earthquake, no storm surge, no landslide warning. Just silence and then absence. Traffic cameras recorded the moment in infrared. At 3:46 a.m., the road is intact, glowing faintly against the cold coastal air. 12 seconds later, the image shudders. A seam opens across the asphalt. Then the ground begins to move, not gradually, not hesitantly, but decisively. The cliff does not crumble, it releases. What had been solid moments earlier accelerates outward and downward, fragmenting into cascading debris before disappearing into black water. By 3:48 a.m., the road is simply gone, erased as if it never existed. By chance alone, no vehicles were on that stretch of highway at the moment of failure. But what followed would make it clear this was not an isolated incident. It was a signal. Within 72 hours, 3 more major coastal failures occurred along a 200-mile stretch of California's shoreline from San Luis Obispo to Monterey. Entire neighborhoods in Pacifica experienced sudden ground subsidence. Streets cracked open, driveways tilted, homes shifted out of square within hours. In Capitola, cliffs that had stood unchanged for decades lost more than 40 feet of elevation overnight. Beaches vanished, backyards became voids. These failures shared one disturbing trait. None were triggered by the events scientists rely on to explain collapse. No heavy rainfall, no storm surge, no seismic shaking. The coast failed anyway. On January 21st, Dr. Gary Griggs, a coastal geologist at UC Santa Cruz with more than 50 years of experience studying California's shoreline, issued a statement that immediately raised alarms across the scientific community. "We are observing cliff failure rates and patterns that have no precedent in our monitoring record," he said. "These collapses are occurring without traditional triggers. Either our understanding of coastal mechanics is incomplete, or the coast itself has entered a new state. That possibility carries consequences far beyond broken roads. To understand why this moment matters, you need to understand what California's coast actually is and what it is not." Much of the coastline between San Luis Obispo and the San Francisco Bay Area is not carved from granite or bedrock. It is composed of sedimentary formations, ancient seabeds lifted upward over millions of years by tectonic forces. Sandstone, mudstone, shale. These materials are strong when dry and intact, held together by mineral bonds formed under pressure. But they are also porous. They contain microscopic spaces capable of holding water. When those pores fill, internal pressures rise. The bonds weaken. The rock loses cohesion, not visibly, not immediately, but structurally. The U.S. Geological Survey has long classified this region as highly susceptible to landslides and cliff failure. But susceptibility does not mean unpredictability. Historically, major collapses followed recognizable patterns. Winter storms saturating cliffs, powerful waves undercutting their bases, earthquakes pushing already stressed slopes past their limits. January 2026 followed none of those scripts. Rainfall during the 30 days prior to the Highway 1 collapse measured just 1.2 inches, far below the January average of nearly 5 inches. Wave heights hovered between 6 and 8 feet, well under the levels associated with erosion-driven failure. No earthquakes above magnitude 2 occurred within 100 miles in the preceding week. And yet, a cliff Caltrans engineers had inspected and rated as stable 6 weeks earlier catastrophically failed. When Dr. Griggs and his team arrived at the Big Sur site later that day, what they found deepened the mystery. The collapse had not originated at the cliff face. It began 40 to 50 meters inland, a deep-seated structural failure, not a surface slump. The exposed rock showed extensive internal fracturing, and those fractures were fresh. They were open, unsealed, untouched by mineral deposits that would suggest long-term formation. Something had weakened the rock mass internally. The fractured rock does not simply collapse on its own. Something had pushed the system past a threshold, quietly, invisibly. Until gravity finished the job, before the team could complete its analysis, the coast failed again. On January 20th at 1:15 p.m., residents of Pacifica heard a deep rumble beneath their homes. Not an explosion, not thunder, something lower, something heavier. Then the ground began to move, cracks raced across streets. Sidewalks warped, driveways slanted toward the sea. Within 2 hours, 6 homes suffered structural damage severe enough to render them unsafe. Foundations split, walls separated, windows jammed into distorted frames. Pacifica had dealt with erosion for decades, but erosion measured in inches per year, slow enough for monitoring, mitigation, retreat. This was different. This was collapse measured in hours. Emergency responders evacuated 34 homes. Geotechnical engineers deployed ground-penetrating radar and discovered something even more unsettling beneath the neighborhood: voids. Cavities where material had migrated or collapsed, leaving empty space where solid ground should have been. Whether those voids formed suddenly or accumulated slowly over years remains unclear. What is clear is that the surface gave no warning before failing. And this was only the beginning. Before scientists could stabilize the Pacifica neighborhood or even fully interpret what lay beneath it, the coast failed again. On January 21st at 6:30 a.m., residents of Capitola, a small beach community just south of Santa Cruz, were jolted awake by a sound witnesses later described as thunder rolling underground. Seconds later, the bluff behind several oceanfront homes began to disintegrate. This was not erosion in slow motion. This was sudden loss. A 200-meter section of coastal bluff collapsed almost vertically, removing nearly 40 feet of elevation in under a minute. Massive blocks of rock, some the size of delivery trucks, detached as a single mass before shattering against the beach below. Dust plumes rose into the morning light. When the noise stopped, the coastline had moved inland by an average of 35 feet. 3 homes lost their entire backyards. 2 were immediately red-tagged as uninhabitable. Decades of gradual erosion compressed into seconds. By this point, coincidence was no longer a credible explanation. Within 4 days, California had experienced 3 major coastal failures, each different in appearance, but all sharing one impossible feature. None had been triggered by the forces scientists are trained to monitor. That afternoon, the California Geological Survey convened an emergency assessment panel. 27 specialists were brought together under restricted briefing conditions: coastal geologists, seismologists, hydrologists, geophysicists, and infrastructure engineers. Their mandate was urgent and unsettling: determine whether the January collapses represented rare, isolated events or the opening signs of systemic coastal failure. The panel began by laying out what they knew. Groundwater levels beneath coastal California had been declining for years, driven by prolonged drought and pumping. Satellite measurements showed subtle but persistent subsidence along portions of the coast, millimeters per year, easily dismissed as noise. Sea level had risen approximately 9 inches along this stretch of coastline since 1990. That change altered where wave energy strikes cliff bases, shifting erosion patterns upward into previously untouched zones. Seismic activity from earthquake sequences in 2020 and 2021 had shaken the region, not violently enough to cause collapse at the time, but potentially enough to create microfractures throughout already stressed rock. Each of these factors had been developing slowly, incrementally, quietly. None explained why failure suddenly clustered in January 2026. That was when Dr. Kang-Hun Jai, a geophysicist from UC Berkeley specializing in subsurface imaging, introduced a theory that reframed the entire event. He called it compound degradation. The idea was disturbingly simple. No single force had crossed a danger threshold. Instead, multiple slow-moving processes, each below detection limits on its own, had accumulated over time. Fractures too small for surface monitoring. Groundwater pressure changes too subtle to register as warning signals. Erosion zones migrating upward without triggering alarms. Added load from roads, homes, and utilities perched above weakened cliffs. Individually, none of these conditions would have justified intervention. Together, they may have reduced the rock mass's strength to the point where gravity alone became sufficient to cause collapse. The coast did not fail because of a storm or an earthquake. It failed because its margin for stability had quietly vanished. If Dr. Kang's hypothesis was correct, the implications were staggering. It meant large portions of California's coastline could be approaching failure without showing any surface signs detectable by current monitoring systems. Rock masses that appear stable, that have passed inspections, hazard ratings, and engineering reviews, may in fact be operating on borrowed time. And when failure occurs, it will not announce itself. It will simply happen. The panel's findings also exposed a critical weakness in how coastal risks are assessed. California's monitoring infrastructure is designed to detect change that accelerates gradually. GPS stations measure slow movement. Laser scanning tracks cliff retreat over months or years. Visual inspections look for cracks, slumping, or surface deformation. These tools are excellent at identifying problems that develop in stages. They are nearly blind to failures driven by subsurface degradation that remains invisible until the final moments. By the time a crack appears on the surface, the internal structure may already be beyond recovery. The consequences became immediately clear along Highway 1. The Big Sur collapse severed the only direct coastal route between Monterey and San Luis Obispo. Detours via Highway 101 added over 120 miles and up to 3 hours of travel time. Emergency response routes were compromised. Coastal communities became partially isolated. Caltrans initially estimated repairs would take 8 to 12 months and cost between $45 and $60 million. But those estimates assumed the surrounding cliffs were stable enough to support reconstruction. Further investigation revealed similar fracturing patterns extending beyond the collapse zone. Rebuilding in place risked repeating the same failure. Alternative solutions, tunnels, bridges, rerouting inland carried price tags in the hundreds of millions and timelines stretching years, all while the geology beneath remained uncertain. In Pacifica, evacuated homeowners faced a different kind of collapse. Mortgage payments continued on properties that could no longer be occupied. Insurance coverage became uncertain. Repair estimates ran into the hundreds of thousands, with no guarantee the ground would stop moving afterward. Insurance companies responded quickly. Several major providers announced temporary suspensions of new homeowner policies in designated coastal erosion zones. Existing policyholders received notices of premium increases ranging from 40 to 300%. Real estate markets reacted immediately. Pending home sales collapsed, contracts were canceled, listings sat unsold. Home equity, often the primary financial asset for families, evaporated overnight. And yet, for many residents, the greatest cost was not financial. It was uncertainty. Is my home safe? Is the ground beneath my street stable? Could this happen here tomorrow? No one could answer with confidence. The January collapses revealed a truth California had not prepared for. Rapid coastal failure does not require dramatic warning signs. It does not need storms or earthquakes or visible erosion. It only needs time and stress and the quiet accumulation of damage below the surface. And if that is how the coast is failing now, then what happened in January may not have been an anomaly. It may have been a preview. By the end of January, one uncomfortable question dominated every closed-door briefing in California. How could 3 major coastal failures occur within days, without a single credible warning? The answer was not negligence. It was not ignored data. It was not outdated engineering. It was something far more unsettling. California's monitoring systems were working exactly as designed. They just weren't designed for this. For decades, coastal hazard management has been built around a simple assumption. Geological failure gives notice. Cracks appear, slopes creep, movement accelerates, sensors register change, humans respond. That model works for landslides, erosion, and gradual bluff retreat. It collapses when failure originates underground. Along much of California's coast, cliffs are composed of layered sedimentary rock, sandstone, shale, mudstone, deposited as ancient seabeds and later uplifted by tectonic forces. These materials are inherently fractured, porous, and sensitive to water pressure. What monitoring systems mostly observe is the surface expression of these materials. What they rarely see is what happens inside them. Subsurface weakening does not announce itself with visible signs. Microfractures open silently. Pore pressures redistribute as groundwater levels change. Cementation bonds that once held grains together degrade slowly, imperceptibly. From the surface, everything appears unchanged. Until it is. At Big Sur, post-collapse imaging revealed fracture networks extending tens of meters behind the cliff edge. These fractures were not new in the geological sense. They likely began forming years earlier, but they were fresh in the mechanical sense. They had widened, connected, reached a critical density. Yet none of this was detectable through standard inspections. Caltrans relies on visual surveys, slope stability models, and periodic geotechnical assessments. These tools are calibrated for identifying known failure modes, slumping, undercutting, rainfall-induced slides. They are not designed to detect strength loss inside intact-looking rock. In Pacifica, the situation was even more revealing. Ground-penetrating radar deployed after the subsidence event detected voids beneath residential streets, cavities where material had shifted or compacted, leaving empty space behind. But radar only works when someone knows where to look. There had been no reason to scan those neighborhoods before the ground moved. From a risk management perspective, Pacifica was already categorized as vulnerable, but vulnerable in a slow, manageable way. Inches per year, decades of warning. What happened in January unfolded in hours. This gap between surface stability and subsurface failure exposes a fundamental limitation in hazard detection. We monitor what we can see, but what caused these collapses was invisible. Seismologists reviewing data from the days leading up to the failures found something unusual, but not alarming enough to trigger action. Low-level seismic noise, signals too weak to register as earthquakes, too diffuse to locate precisely, often dismissed as background activity, ocean wave interactions, distant human activity, atmospheric coupling. In hindsight, these signals may have represented microfracturing within stressed rock masses, but without a known framework to interpret them as danger, they were lost in the noise. Dr. Kang Jai's team proposed adapting techniques used in earthquake early warning research to coastal monitoring. Dense arrays of ultrasensitive sensors could detect subtle changes in wave propagation through rock, a sign that internal structure is degrading. In theory, this could provide advance notice. In practice, it raises uncomfortable realities. Covering California's coastline with such systems would require thousands of instruments. Installation alone would cost hundreds of millions of dollars. Data analysis would demand continuous processing by advanced algorithms trained to recognize patterns scientists are only beginning to understand. And even then, the warning might be measured in hours. Not days, not weeks, hours. That changes everything. Emergency management depends on time. Evacuations, closures, infrastructure shutdowns all require planning windows longer than the failures observed in January. When collapse occurs faster than response, risk becomes unmanageable. This reality collided with infrastructure planning almost immediately. Highway 1 was built under the assumption that cliff retreat would be gradual. Repairs could be scheduled, reinforcements added, routes adjusted over years. That assumption no longer holds. Engineers examining adjacent sections of the highway discovered areas where rock strength had declined significantly without visible surface deformation. In other words, the highway was still standing, but its foundation may already be compromised. Rebuilding in the same place without addressing subsurface conditions risks repeating the disaster. Yet addressing subsurface conditions requires tools that largely do not exist at operational scale. This creates a paradox. California's most valuable coastal infrastructure sits atop geology that cannot be reliably monitored with current technology. The systems designed to protect people and assets are blind to the processes now driving failure, and the consequences extend beyond roads and homes. Coastal wastewater treatment plants, power lines, fiber optic cables, emergency access routes all depend on ground stability. As insurers reassessed risk models, their conclusions mirrored those of scientists, but with faster timelines. Risk had become unpredictable. An unpredictable risk is uninsurable. Premiums surged, coverage shrank. Some properties became effectively uninsurable overnight. Without insurance, mortgages become vulnerable. Without mortgages, property values collapse. A geological process had triggered a financial one. Local governments found themselves caught in the middle. Declining property values meant reduced tax revenue, just as emergency costs were rising. Evacuation planning, infrastructure assessment, legal disputes, and social services all demanded funding. Yet the core question remained unanswered. Is January 2026 the beginning of a new pattern? Or was it a rare convergence unlikely to repeat soon? Some officials leaned toward optimism. The coast had been quiet since January 22nd. No additional major failures had occurred. Perhaps the system had released accumulated stress. Others, including Dr. Griggs and Dr. Kang, warned that this interpretation was dangerous. Geological systems do not release stress cleanly. They redistribute it. A collapse in one location can alter stress fields in adjacent areas. Groundwater flow paths change. Load shifts occur. What stabilizes one section may destabilize another. The absence of immediate failures does not indicate safety. It indicates uncertainty. The truth is, California's coastline was developed during a period of relative geological calm. Sea levels rose slowly. Groundwater systems were stable. Human loads were manageable. Those conditions are changing, and the monitoring systems designed for the past may not be capable of protecting the future. The question is no longer whether failure can occur without warning. January proved that it can. The question is whether society can adapt to risk that announces itself only at the moment of collapse. Because if not, then the most dangerous places on the coast are not where the land is visibly crumbling. They are where everything still looks solid. By early February, the geological crisis had become something else entirely. A human one. Evacuation orders remained in place across parts of Pacifica. In Capitola, red-tagged homes sat abandoned behind temporary fencing. Along Big Sur, Highway 1 closures had turned coastal communities into near islands, accessible only by long inland detours. But the most destabilizing impact wasn't the collapsed cliffs. It was uncertainty. People could accept danger if they understood it. Flood zones, fire maps, earthquake faults. These risks had boundaries, probabilities, mitigation plans. This risk had none. Residents asked officials the same question over and over. Is my home safe? No one could answer honestly. Coastal hazard maps, long used to guide development and insurance decisions, suddenly felt obsolete. They were based on historical erosion rates, known landslide zones, and surface indicators. They did not account for rapid subsurface failure. Entire neighborhoods now existed in a gray zone, not actively collapsing, but not verifiably stable. That gray zone is economically toxic. Banks require certainty, insurers require models, homeowners require reassurance. None were available. Mortgage lenders quietly began tightening requirements for coastal properties. Appraisals reflected elevated risk. Refinancing options disappeared. Home equity, the primary source of wealth for many families, began to evaporate. Some owners tried to sell. Buyers vanished. Real estate listings in affected coastal zones sat untouched or received offers so low they amounted to forced abandonment. People who had planned to retire, downsize, or pass homes to their children found themselves trapped, unable to sell, unable to stay, unable to rebuild. For renters, the crisis looked different but felt just as sharp. Evacuations displaced families into already strained housing markets. Short-term rentals surged, temporary shelter stretched into months. Communities began fragmenting, and while individuals struggled, governments faced a deeper dilemma. For decades, California's coastal strategy relied on a balance between protection and retreat. Where erosion was slow, engineering solutions bought time. Where it accelerated, managed retreat programs allowed gradual relocation. That strategy depends on predictability. January shattered it. How do you manage retreat when failure can occur anywhere, without warning? How do you justify public spending on buyouts when you cannot identify which properties are truly at risk? Every dollar spent on relocation is a dollar not spent on schools, healthcare, wildfire response, or drought mitigation. And yet delaying action risks catastrophe. Officials recognize the cruel math almost immediately. There are millions of coastal properties. Only a fraction can ever be protected. Only a fraction can ever be bought out. Choosing which communities to save and which to abandon is politically explosive, and the science offers no clear guidance. Emergency planners began running worst-case scenarios. What if a collapse occurred during peak tourist season? What if Highway 1 failed during daytime traffic? What if a coastal evacuation route itself collapsed during an evacuation? These were not hypothetical questions. They were logistical nightmares. Many coastal towns are connected by a single road carved into cliffs. When that road fails, residents are trapped between unstable land and the ocean. Helicopter evacuations are limited. Sea evacuation depends on calm conditions. Nighttime failures offer almost no escape options. The infrastructure was never designed for this kind of risk. In retrofitting, it may be impossible. Engineers explored alternatives, tunnels bored through mountains, bridges spanning unstable zones, rerouted highways inland. The costs were staggering. Hundreds of millions per segment, years of construction, environmental impacts that would trigger lengthy legal battles. And none of it addressed the root problem. The land itself is becoming unreliable. At the state level, lawmakers faced mounting pressure to act, but no consensus on how. Some pushed for aggressive retreat policies, expanding buyout programs and banning new coastal construction outright. Others warned that abandoning the coast would devastate local economies and surrender some of the most valuable real estate in the country. Tourism, fisheries, ports, and coastal industries depend on access and stability. Walking away is not a simple choice. Insurance companies made their position clear through action, not words. Coverage restrictions spread beyond the January failure zones. Risk models were adjusted statewide. Premiums rose even in areas that had not yet experienced collapse. From an actuarial standpoint, unpredictability equals exposure. From a homeowner's standpoint, it equals fear. People began noticing cracks that may or may not matter, small shifts indoors, hairline fractures in driveways. Normal settling suddenly felt ominous. Psychological stress spread faster than erosion ever could. In Pacifica, residents described sleeping in shifts, listening for sounds beneath their homes. In Capitola, people avoided the edge of their properties, unsure where solid ground ended. This kind of anxiety changes behavior. Communities lose cohesion, trust in institutions erodes, rumors spread faster than facts. And all the while, the coast looked deceptively calm. Waves rolled in, sunsets burned orange across the horizon. Tourists posed for photos at overlooks above fractured rock. Nothing about the surface suggested imminent danger. That disconnect between what people see and what science suspects is perhaps the most dangerous element of all. Humans are wired to respond to visible threats. Firestorms, floodwaters rising. Invisible risk breeds complacency until it suddenly becomes catastrophe. State agencies increased monitoring, but even officials acknowledged the limits. Instruments can measure movement, pressure, vibration, but they cannot predict exactly when a threshold will be crossed. Geology does not issue countdowns, and once failure begins, it cannot be stopped. Some policymakers began floating an uncomfortable idea. What if the goal is no longer protection? What if the goal is survival? That would mean redefining coastal living entirely, accepting that some places will become temporary by default, that ownership near the ocean may no longer mean permanence. It would require a cultural shift as much as a technical one. Americans built coastal communities on the belief that engineering could hold the line. That belief has deep roots: levees, seawalls, dams, highways. The cliffs are not walls, they are systems, and systems can fail silently. By mid-February, one thing had become clear. The January collapses were not just a geological anomaly. They were a stress test of infrastructure, of governance, of economic assumptions, of the idea that risk can always be managed with enough data and planning. The coast was forcing a reckoning, and in that reckoning lay an uncomfortable truth. We may not get to choose where the next failure happens, only how prepared or unprepared we are when it does.